our first unit here in E&M. Let's get right into the material, okay? I'm gonna let some footage from Physics 2 play. First, central to our understanding of electrostatics is our understanding of charge and how it behaves, okay? So what is charge? All right, you can have a positive charge or you can have a negative charge. An atom has protons and electrons in it. Protons residing in the nucleus, electrons being in a cloud around the nucleus. A proton, we would say, has a +1 charge and an electron has a -1 charge. Now, what I'm trying to demonstrate to you is that a proton and an electron have the same magnitude of charge. One is +1, one is -1, but the absolute value of charge is still 1. The specific charge of an electron is found on your reference table at the very top, and it's denoted by a lowercase e. It is denoted electron charge magnitude. Lowercase e equals 1.60 times 10 to the -19 C. Now what is C? That's a unit you haven't seen before. Big C, it's a capital C, stands for coulombs. The unit of charge is the coulomb, okay? If someone tells you I have 1 coulomb of charge, that describes a precise amount of charge which you have. We get that 1 coulomb is equal to the charge on 6.25 times 10 raised to the 18 electrons, okay? Therefore, 6.25 times 10 to the 18 electrons gives you 1 coulomb of charge. Coulomb is a scalar quantity. You can also say that 1 kilocoulomb is equal to the charge on 6.25 times 10 to the 18 protons. Have you ever taken a balloon, rubbed it against your hair, and now your hair becomes attracted to the balloon? Okay, let's draw a picture of that. There's some fuzzy hair on this person right here, and there's a big old balloon. Now, when you rub the balloon against your hair, charges are exchanged. Some charges leave your hair and go to the balloon, okay? So you might say that in this exchange, when you're rubbing the balloon against your hair, negative charges go from the balloon to your hair. Okay, so let's draw this like a negative charge leaves the balloon as you're rubbing against your hair, and the hair basically takes that negative charge off the balloon. You might be asking yourself now, wouldn't the same process also be done if positive charges went from the hair to the balloon? And my answer would be yes, you would receive the same result. However, this is not possible. Okay? Why is that not possible? Because the structure of materials is such that the materials are made up of atoms, and in each of those atoms you have a positively charged nucleus, and much further out of the atom, at the edges of the atom, you have your electrons. If I were to draw an atom for you right here with the tiny nucleus in the center and some electrons floating around at the edges, you could see that it is much easier for you to pull an electron away from the atom than it is to pull the nucleus, the big heavy nucleus right in the middle of the atom. It's like if I had a boulder that was 2 feet in diameter and I was trying to take off little pieces, tiny pebbles from the edge of the boulder versus trying to get a steel ball from the center of the boulder, okay? You'd have to destroy the entire boulder in order to get to the steel ball at the center, the steel ball representing the nucleus at the center of an atom. The nucleus of an atom never moves. And given that truth, if the nucleus of an atom never moves, that means positive charges can never move. Only negative charges can move. Only electrons can move. So if electrons are moving from the balloon to your hair in this case, that means your balloon becomes electron deficient. If it becomes electron deficient, if it loses electrons, then it gains a positive charge. You cannot give something a positive charge by giving it protons, because protons don't move. You have to give something a positive charge by removing electrons. And therefore, since the electrons are being given to the hair, your hair becomes negatively charged. That is what is happening when you're doing the rubbing. okay? But you will notice that when you're done rubbing, the balloon sticks to your hair. The balloon is attracted to your hair. Positive charges attract negative charges. That is sort of the central fact, the central idea of all of electrostatics and circuits, is that positive charges attract negative charges and like charges repel. So positive attracts negative, negative repels negative, positive repels positive. It's like magnets. Pretty intuitive. Since a positively charged item will attract a negatively charged item, the balloon now sticks to your hair. We need to understand why these materials are able to do this, okay? And that brings us to our discussion of conductors, and you have insulators. I don't know how to spell insulators, but you get the idea, okay? So like I discussed previously, the positive charges inside any substance, any solid, let me be more specific, the positive charges in any solid will never move. The electrons, however, in a conductor are free to move. So we're talking about electrons here. The electrons in insulators are not free to move. In an insulator, you would need to apply a pretty significant force, like you do when you rub the balloon against your hair, in order to get electrons to move from one surface to the other, okay? And if we zoom in on the balloon, only the electrons from the surface of the balloon can be abstracted from the balloon. The electrons further inside, since they're not directly touching your hair, cannot be abstracted because you need a physical force to pull the electron away from the insulator. So when you rub two insulators together, the exchange of charge is only pulling the charge from the edge of one and giving it to the edge of the other. You cannot touch charges that are more protected in deeper layers of atoms inside the substance. So I'm sure we can all understand what examples of insulators and conductors are. Conductors are things like metals, like salty water. Insulators are things like the wooden desk that you're probably watching this on. They're things like cotton, plastic, glass. So this experiment is very often repeated and very often illustrated on the AP exam, not with hair and a balloon, but rather with a glass rod and a silk cloth, okay? I've got quite a funny story about glass rod and silk cloth. We'll save that to the end. Where was I? Okay, conductors and insulators. The only reason that the positive charge that is built up on the balloon is allowed to stay on the balloon is because the balloon is an insulator. And the only reason that the negative charge on your hair is allowed to stay on your hair is because your hair is an insulator. If I had a conductor, like a big block of iron, and another conductor, like a big block of steel, and this one had a positive charge and this one had a negative charge, if I brought the two together and I touched them to each other, what do you think is going to happen? All the electrons from the negatively charged block will flow to the positively charged block because they're conductors and the electrons will freely move between them. Therefore, if I touch two charged conductors together, we're going to have a flow of electrons, and within a few milliseconds, or a few nanoseconds, more realistically, the two blocks will become neutral and they will lose any charge they originally had. That's why this is possible only with insulators. I want us to pay attention to this example I just gave us for just a little bit here, okay? I mentioned that if you touch two charged conductors together, electrons will move from one to the other, okay? Does anyone know what electricity is? Electricity is the movement of electrons. Here, we have a movement of electrons from the negatively charged brick to the positive one. Therefore, here we have electricity. A movement of charge is electricity. It is a current. Moving on from there, now that we understand fundamentally how charges behave, we can use Coulomb's law, okay? Coulomb's law helps us to quantitatively define how they behave. Coulomb's law is an equation stating that the electric force being a vector, is equal to 1 over 4 pi epsilon times Q1 times Q2 over R squared. okay? And these are magnitudes. Let's break down what this is telling us. First of all, epsilon naught is a constant. Epsilon, being a constant, can be found on the first page of your reference table. It is the vacuum permittivity, 8.85 times 10 to the negative 12, okay? Now also on your reference table, you are able to see the Coulomb's law constant K. K, as shown on your reference table, equals 1 over 4 pi epsilon, which is also equal to 9.0 times 10 to the 9. So therefore, this equation of Coulomb's law can be rewritten as such. The magnitude of the electric force vector equals K times Q1 times Q2 over R squared. So the electric force. What is the electric force? A positive charge exerts a attractive electric force on a negative charge. So if I were to draw that out for you, positive and a negative charge, the positive charge exerts an attractive electric force on the negative charge, and because of Newton's third law, the negative charge exerts an equal and opposite attractive force on the positive charge. So this attractive force, or in the case of two like charges, this repulsive force, is defined as the electric force, okay? The equation provides us with the magnitude of the electric force. What does magnitude mean again? It means that instead of giving us the vector, instead of giving us the direction, it's only going to give us the value of the electric force, okay? If, let's say, I plugged into my equation and I got a value of 10 newtons for my electric force, I would not immediately know which direction that is being applied in. I would plug into my equation, I'd find the magnitude, 10 newtons, and then I would reconsult the problem. I'd reconsult my drawing and I'd say, okay, I'm dealing with a positive charge and I'm dealing with a negative charge. Therefore, this 10 newtons that I was given by my equation is an attractive force. So relative to the positive charge, this is a 10 Newton attractive force pulling me in this direction. I would reconsult my problem and I would see two negative charges. Therefore, my 10 Newton value is a repulsive force acting in this direction if I am considering this particle, or if I'm considering this particle, it's a repulsive force acting in this direction. Back to the rest of our equation. Again, K is a constant. It is a constant available on your reference table. In the electrics unit, Q is the symbol of a point charge. What is a point charge? That's a point charge. It's a charge that has a position, meaning if I set these two charges up on a number line, I could define the positive charge at position -2, and I could define the negative charge at position +2. You'll see later, in probably the next unit, when we're dealing with capacitors, we have a capital Q that we're dealing with. Capital Q is just charge. That capital Q is used when we have some amount of charge that we are not able to assign a exact position to. We just have some charge, okay? But that's not what we're dealing with here. And the final component in our equation, R squared. Again, we might remember from previous physics classes or from previous units that R is a value which determines length, okay? Therefore, R being the distance between our two charges. In this case, our distance between the two charges is 4. So therefore, our R would equal 4 and our R squared would equal 16, okay? Again, every equation simplifies down to something really easy once you know what to plug in for all of the equations. Moving on from there, we have a few more complicated examples of the rubbing the hair on the balloon bit. So we're going to be considering that at a much more atomic, much more zoomed in level. I am going to charge a glass rod, which I'm going to denote like this, with a cloth, okay? Let's call this my cloth. And I'm rubbing the cloth backward and forth until the cloth is able to pull electrons off of the glass rod, which means the cloth becomes negatively charged, glass rod becomes positively charged. I have a glass rod that's positively charged. Let me draw this right here. Since the glass rod is since the glass rod is an insulator, charge is not able to move throughout it, okay? So a great example of that is if this is the entirety of my glass rod and I only rub the glass rod between these 2 points, like I only rub the glass rod in this area, it means that only this area of the glass rod will develop a positive charge, okay? If my cloth never touches this section, it means this section is still neutral, okay? So let's continue with that in mind. Let's just say that my cloth only scraped against the rod in this area. So only this top section of my rod will bear a positive charge. In the case of something like a conductor, this would not be possible, because in a conductor, electrons from the neutral side will be conducted to the positive side. Reason for that being is that in a conductor, coulombic forces between particles are able to act on each other. If I have a large concentration of electrons down here, those electrons are going to repel one another. And if they repel one another, they're going to want to spread out as much as possible. So they're going to diffuse upwards into this area where there is comparatively fewer electrons. They're going to move from a place with a lot of repulsions to a place with few repulsions. So that is a more stable, a more favorable thing for them to do. However, in an insulator, they're locked in place. They can't move, even if they are experiencing a lot of repulsions. Let's reassume that this is an insulator, okay? And let's say that I were to bring a block of steel here, steel being a conductor. The electrons in a conductor are free to move about however they please. The positive charge on this rod, if I bring it closer to the steel brick, let me draw it so that you can see what I'm talking about. If I bring it much closer to the steel brick, the positive charges on the rod are going to attract the electrons within the conductor. So that means the electrons from throughout the conductor are going to be pulled towards this end, and they're going to be concentrated on this end. Okay? Which means there will be comparatively fewer electrons on the right. Recall that positive charges do not move. Positive charges can't move. Okay? So if in the block there is now many, many more electrons on this side, that means there are many fewer electrons on this side. So if you have the same amount of positive protons with fewer electrons here, that means this side has developed a positive charge and this side has developed a negative charge, okay? However, this is a temporary charge arrangement, which means if I remove the glass rod, the charges will restabilize back into the neutral configuration of the brick. So going from there, we've covered how to charge insulators, how to give insulators a permanent charge. How do we give conductors a permanent charge? Because you can't rub a piece of cloth up and down a steel rod because the electrons would just conduct back. Because if I were to take this glass rod and I were to touch it to the conductor, then electrons from the conductor would flow into the glass rod, and the charge on the glass rod will become less positive. And since electrons are flowing out of the conductor and into the glass rod, since they're touching, the conductor will develop a small positive charge. Another way of doing that is if I have my same positively charged glass rod and I were to have a conductor like this, I could connect this conductor to ground. This is the symbol for ground. Now, what is ground? Ground in this class is going to be defined as a place that is an infinite source and sink of electrons. What do those two words mean? An infinite source of electrons, I think that's pretty intuitive. You can pull as many electrons as you want from ground. A sink, an infinite sink of electrons, means you can donate as many electrons as you want to ground. Let's go back here for a minute. I took a positively charged rod and I touched it to a conductor. What was my result? the positive charge on my rod diminished, but my rod is still positively charged, and my conductor gained a positive charge. Okay? In this example, I have a neutral conductor and a positively charged rod, and this positively charged rod is attracting electrons to the left side. Okay? It's attracting the electrons in the brick to the left side, just the same as in the example before. However, the left side is developing a negative charge and the right side is now developing a positive charge, just like in the example before. However, now that the right side has developed a positive charge, it is attracting electrons from ground. So that means new electrons from ground are being pulled through the wire and they are coming into the block. So new electrons are coming in to replace all the electrons that left and moved to the left side, all right? Such that this positive charge disappears, and I'm now left with just a negative charge concentrated near the positively charged rod, okay? So I have just a negative charge left on my block. If I remove the rod, all of the negative charge will flow back into ground and I'll be left with a neutrally charged brick. However, if I disconnect ground and then remove the rod, there will be no place for the negative charge on the block to go. Therefore, I'll be left with negatively charged brick of metal. These are kind of the more important. Let's discuss the law of conservation of charge. It's derived from the law of conservation of energy, but we're not going to get right into that right now, okay? Conservation of charge is pretty simple. It's the same as conservation of mass. It's the same as conservation of energy. It states that in any closed system, let's remind ourselves what a closed system is. A closed system is a system in which every interaction that might affect anything in the system is included in the system. So if we were considering the system in which I am punching this wall, in order to account for all interactions and all energy, we would need to define the closed system as including the wall, myself, the floor that is supporting me, and the rest of the house that is supporting the wall, okay? I would not be able to punch the wall if I were not grounded on the floor beneath me. Because, like I said, if I tried to push against the wall like this, I would start floating towards the right if I wasn't securely grounded on the floor. And if I punched the wall would just shoot through and continue moving unless the rest of the house was there to keep it in place, okay? So what a closed system is you have accounted for every particle, every interaction that might affect your system. Okay? Conservation of charge means that in any closed system, you must start and end with the same amount of charge, always. If I started with 0 charge, I'm going to end with 0 charge. And 0 charge can take on many forms. It could be +3 coulombs and -3 coulombs. And that's still 0 charge, conservation of charge. If I start with 3 coulombs of charge, if I start with 3 protons in my system, I'm going to need to end with 3 coulombs of charge, which might be +5 coulombs and -2 coulombs. From there, we get into the really equation-y and mathy stuff. It's best to consider this with respect to a diagram. If I have a charge here in the center that is +10Q, then that charge creates an electric field around it. What is an electric field? It's the same thing as a gravitational field, wherein if you have an object of mass, an object that has mass, and you place that object in the gravitational field, then that object will start being attracted to whatever's creating the gravitational field. Take Earth, for example. Earth emits a gravitational field. If suddenly you put your teacher 10 miles above the Earth, you're putting your teacher in Earth's gravitational field, and the teacher will fall towards Earth. Same thing in the electric field. If you have a charge, that charge emits an electric field around it, wherein if I were to place another charge let's say minus 10q, that charge would fall towards the plus 10q charge. When we are dealing with fields and forces and electric potential, which we haven't gotten to yet, don't worry, we say that the positive direction, recall that in Physics 1, whenever we're dealing with vectors, we need to assign which values are positive and which values are negative. We say that the positive direction is the direction in which a positive charge would move. Which means if I were to place a positive 10 coulomb charge right here, that being a positive charge would move in this direction because it is being repelled by the other positive charge. Therefore, we can say that the electric field vector coming from this charge radiates outward like this. Just like the gravitational field, it radiates outward in 3 dimensions in all directions. You can have an electric field generated by a negative charge, negative 10q. And if I were to place a positive charge right here, that positive charge would be attracted to the negative charge. Therefore, drawing the electric field lines for a negative charge, you would draw them like this, converging in 3 dimensions from all directions towards the center. Like you are given an equation for electric field. You're given that the magnitude of the electric field is equal to the electric force divided by the charge Q. Electric field is equal to K Q1 over R squared. And you can see why these equations are equivalent, because the electric force is K Q1 Q2 over R squared. And if we divide this by Q, you get K Q1 over R squared, where K is again the Coulomb's law constant. Q1 is your charge that you've placed in the center, and R squared is the distance you are from the center, okay? Meaning electric field is evaluated at our particular point in space. So the electric field here is going to be different from the electric field here, okay? So you need to specify a point in space at which you are evaluating the value of the electric field. Since the electric field radiates out equally in all directions in 3 dimensions, you could say that a point where R equals 10, let's say R equals 10 is a point right here, and R equals 10 also defines another point right here. They are the same distance away from our central charge, therefore they will experience the same electric field. We can draw a line around our center charge that is supposed to be a perfect circle. We can draw a line around our center charge with our center charge in the center, where every point on that line will have the same exact value for the electric field, because they will all be the same distance from the center charge. This circular line that, let's pretend that the central charge is at the center of this line is called an equipotential line. We're going to get into electric potential right after this, but what we're trying to say is that every point on this line experience the same electric field, so it is an equipotential line. So therefore there are a series of equipotential lines, each with a smaller and smaller electric potential, or a smaller and smaller electric field. Okay? But the important characteristic about this is that at all points, your equipotential line is always perpendicular to your electric field vector. Since your equipotential line is a circle, it is not a vector, and therefore doesn't have an arrow next to it. From there, you may run into a situation where you might need to consider the electric potential from 2 or more charges, okay? If I have a charge here that is plus 10q, and I have a charge here that is plus 10q, the lines that radiate outward representing the electric field will radiate outward in both directions from each, as such that if you place a charge exactly in the middle of the two, that charge will not move, because the charge is being repelled by this one and it's being repelled by that one. So it's like 2 magnets trying to repel each other. If you place one on top of the other exactly right, the two magnets aren't going to move because their forces are balanced. The force acting on this positive charge from this center is the same as the force acting on the positive charge from this center, so the forces will be balanced, and therefore it won't move. Therefore, we can draw an equipotential line that is exactly halfway between them, like that. And the equipotential line will again begin to curve around like this, as such. If we are given a plus 10Q and a minus 10Q, then our electric field lines will go in a single direction, one to the other, one arrow, like this. In this example, there is a point exactly in the center where the electric field is 0, meaning that a particle placed there would experience 0 electric force. However, in this example, there is not a point anywhere in the plane where the electric field is 0, because you're going from a positive to a negative. The electric field will always force you to go from the positive charge to the negative charge. Moving on from there, we have electric potential, capital V, also known as voltage, okay? Electric potential has units of joules per coulomb. You'll notice why those units are important in just a moment, okay? Let's say, again, that I am dealing with a charge of plus 10Q. I'm going to come back to this demonstration in just a moment. Let's go back to voltage right now, or electric potential. Your electric potential is again given by your constant times your charge Q, which will be your central charge that you are dealing with, divided by the distance from that central charge. Okay? Again, potential is evaluated at a particular point. And like electric field, electric potential has isolines, lines at which the electric potential are always constant. Even though electric field and electric potential both have isolines, the electric field isolines are not the same as the electric potential isolines, even though they look the same. In AP Physics 2, anytime you are asked to draw isolines, it's always going to be the electric potential isolines. Anyway, let's move on from there. Since both of these appear to behave in the same way, why do I need to care about these two quantities? What's the difference between them? Electric field, like I said before, electric field is a determinant of the electric force acting on a particle. Okay, if I placed a positively charged particle right there, there would be an electric force that acts on the particle, pushing it away. The electric force acting on any particle is given by the charge Q on that particle multiplied by the electric field. And that's exactly the equation we're given right here. The electric field times Q is the electric force acting on that charge, okay? In a similar light, electric potential is a determinant of the potential energy of a particle at a given point, okay? So again, let's draw our electric potential isolines. And electric potential is not a vector, therefore you cannot draw electric potential vector lines. Keep that in mind. Electric potential is not a vector. If I were to put a positively charged item right there, it would have a lower electric potential than if I had a positively charged particle right here, because electric potential is inversely proportional to 1 over r. Or directly proportional to 1 over r, inversely proportional to r. Okay? So as I get further away from the charge, my electric potential decreases, and therefore my electric potential energy decreases. So let's introduce that equation. Your change in electric potential energy is equal to your charge times your change in electric potential, or your change in voltage. Potential energy being in units of joules, charge being in units of coulombs, electric potential being in units of joules per coulomb. We can see why that makes sense. Change in voltage is not a vector because energy is not a vector. Electric field is a vector because force is a vector. And that is the relationship that they have to each other. One is a determinant of the other if you provide a charge into the equation. Now, understand that these equations can also work for the opposite charge. If I have a negative charge that is placed right here, the negative charge will want to move towards the positive center. So that negative charge, since it has a negative Q, will result in a negative potential energy. Since the electric charge will be moving this way, change in potential equals final potential minus initial potential. So we discussed that potential is always greatest nearest to the center. So if a particle moves this way, closer to the center, then your change in potential is positive, because your final is greater than your initial. What kind of particle would be moving this way, towards the center? That would be a negative particle. So a negative charge Q times a positive delta V would equal a negative change in potential energy. And the inverse is true for the positive particle. For a positive particle, you are being repelled, you're moving this way. Your final electric potential is less than your initial electric potential, therefore your change in electric potential is going to be a negative. So given that your change in electric potential is negative for a positive charge, you can say that your change in electric potential energy is going to be your positive Q times your negative delta V, meaning your change in potential energy is still a negative. It's a negative for both cases, whether you put a positive charge or a negative charge there. Why is the change in electric potential energy always negative? Because your electric force will always act on the particle to accelerate it. The electric force will always act to do work on the particle, right? It's the same as, why does your gravitational potential energy always decrease if nothing is holding you back? Because your gravitational force will always act to do work on a non-stationary object. Which means if I place a positive charge right here, these two charges are going to repel each other, and the charge I placed right there is going to gain kinetic energy. Where is it going to gain the kinetic energy from? It's going to gain the kinetic energy by a loss in electric potential energy. And the inverse is also true. So a very important concept from that video that I want to drill into everyone's head right now is the idea of an electric field, particularly inside a conductor. So we have our equations for electric field, electric force, and all of that. But if, let's say, I have a conductor, let's say I'm really zoomed in on some copper wire right here, a conductor, and let's say there is an electric field inside the wire that's pointing in this direction. It's driving positive charge this way, okay? That means that if there is an electric field inside a conductor, there is charge moving through that conductor, okay? An electric field is pretty much like an acceleration onto a charged particle. If you have an acceleration and you're in a conductor, it means the charge is moving, okay? The only case in which you have an electric field and charge is not moving is when you are looking at an insulator. If you're dealing with vacuum or if you're dealing with a conductor, E field moves charges. So if there is an electric field that is acting on this conductor and the conductor is isolated, meaning there is nowhere for charges to flow, this is literally just a hunk of wire that isn't connected to anything else, how will the charges inside of the conductor respond to, let's say, an electric field that has a vector like this? So how will the charges respond to an electric field like this, okay? First of all of the positive charges will begin to collect on the bottom side of the conductor as they are forced to do so by the electric field, okay? And all the negative charges are being forced upward by the same electric field. Such that if we consider the inside of the conductor, there is zero electric field. How do I know there's zero electric field inside the conductor? Because the charges aren't moving. If I have electric field inside a conductor, there must be a movement of charge. So if I apply an electric field outside, the charges will move to perfectly counteract that electric field. The charges inside a conductor will perfectly arrange themselves so as to counteract the electric field and create a zero net field inside the conductor. Another example that is of note is if I look at the cross section of the conductor, I look at it from this side, if there is an excess of positive charge inside of that conductor, the positive charges will repel each other and they will try to get as far away from each other as possible. Therefore, positive charges will collect on the outer rim of the conductor, and the negative charge will mostly remain at the center, okay? The same thing for negative charge. If I have an excess of negative charge inside a conductor, negative charges will repel each other and arrange themselves such that they are the furthest possible distance away from one another. Now that we've got through that, let's review some probably new concepts with the Physics C Electricity and Magnetism course. So this concept is going to look very similar to the center of mass theorem from mechanics, and for good reason, okay? If I were to have, let's say, a sphere right here, and this sphere has a net positive charge, there's an excess positive charge, let's call it plus 4q. This sphere has a charge of plus 4q. It means that, let's say this is a conducting sphere. If this were a conducting sphere, then the positive charges would be uniformly distributed throughout the shell of the sphere to try and get themselves as far away as possible. If it were a non-conducting sphere, an insulating sphere, then it would have some charge density, okay? But regardless of how charge is distributed throughout the sphere, if I am at some point outside the sphere, let's say I have a positive charge right here, this positive charge sees this positively charged sphere, and when we do our force calculations, the electric force equals k q1 q2 over r squared. When we do the electric force calculation, the r squared, the distance between the two charges, can be thought of as being between the charge and the center of the uniformly charged sphere, almost like it was the center of mass, okay? So I'm often going to refer to this as the center of charge. The course and exam description does not refer to it that way, but I think it's a much more descriptive way of visualizing why we're treating this point as the distance from the charge to our sphere. Okay, I'm going to call this the center of charge because it can be interpreted as the point at which all of our charge is concentrated when we are observing it from outside the sphere. Okay? And we're going to talk about a much more complex example of that in just a moment. So from there, we move on to the very calculus-heavy stuff. And this is going to be E-field, electric field. Okay? So if we consult our Physics E reference table, we see the integral form of the electric field equation. The electric field vector at some given point is equal to 1 over 4 pi epsilon, which is the same as our Coulomb's law constant k, times the integral of dq over r squared in the r hat direction. Let's understand what this integral means in the context of our algebraic equation. And one more thing. If you haven't already watched the introduction to Physics C, I highly recommend you watch that because that's going to introduce you to the types of calculus concepts that we're going to need to apply in these classes. Okay, I probably associated with both the mechanics and the E&M playlist, but just watch the Physics C intro video. It's going to be very helpful to understand the calculus concepts. So we can observe this integral here as being an integral of dq, an infinite sum of infinitely small charge, which gives us our total sum of q. So we understand why these two are going to be equivalent, okay? Now, what is r hat? R hat is a unit vector, another topic we covered in the introductory video, and it's basically asking us what portion of this equation, what portion of the electric field contribution is in the r hat direction. Okay, r hats is it specifies a direction. So if I were trying to calculate the electric field between these two charges, the r hat direction, the direction I'd be concerned with, is the direction from one charge to the other. We would use this to understand the electric field contributions from items that are not a point charge, for items that we cannot consider as having a center of charge like this. An example would be if I were to draw a ring, okay? A charged ring. And if I were to analyze it from another dimension, I were to draw my ring like this, and that ring would have a center, and consequently a center axis, perpendicular to the plane of the ring, okay? Think of it like this is my ring, this solid black line is my ring, and this dotted line is the axis perpendicular to the ring. That is what I'm trying to illustrate for us all here, this being my center. So here's going to be our setup for the problem. We have our single point in space P here, okay, at some distance x away from the center of the circle, and the point P is on the same axis as the center of the circle. The circle has some radius a, and therefore if we draw the right triangle here, the distance between our point P and the edge of the ring is going to be r. And we discussed that this was a charged ring with uniform charge density with a total charge of big Q. Okay, and our job here is to find the net electric field experienced at point P and to give our answer in terms of Q, X, and R. Okay? And, of course, universal constants. The first place we got to start is we need to say our electric field at point P is going to equal our Coulomb's law constant K times the integral of the dq over r squared in the r hat direction. So the way we're going to do this is we're effectively taking infinitely small slices of the circle and we're summing up the charge in all those slices in order to get the total charge electric field contributions for the whole ring, okay? So first of all, we need to introduce a topic that probably everyone from mechanics dreads, lambda, okay? Now, lambda is going to be our linear charge density, all right? So you may notice that we weren't given a linear charge density. No, we weren't. However, we were given that there is a uniform density. Therefore, lambda, being our charge density, is the derivative of charge with respect to length. If it's a uniform charge density, then the derivative of charge with respect to length is just the total charge over the total length. So what is the total length of my ring right here? Well, it's going to be the circumference. Circumference equals 2 pi r. In this case, the radius of my ring is a. So circumference equals 2 pi a. Therefore, lambda equals dq dl equals q over 2 pi a. Okay? So therefore, we can say that dq equals big Q over 2 pi a dl. So I'm going to rewrite this integral. The total electric field at point P is going to equal K times the integral of lambda dl over r squared in the r hat direction. So now let's take a look at this circle very carefully, okay? We'll notice that since our r, our distance vector r, is pointing in a direction that isn't exactly parallel to P, we'll notice that it has some contribution like this, okay? So if we resolve that electric field vector into components, we'll see that it has some electric field contribution in the y direction and some electric field contribution in the x direction, okay? But if I were to consider a point here that is exactly opposite r, we'll notice that it also contributes an electric field in the x direction as well as in the y direction, where the electric field contributions in the x direction add, while the electric field contributions in the y direction perfectly cancel. Therefore, since the y directions cancel, we're only concerned with the electric field in the x direction. So now that we know our direction, we can replace our r hat with something that will give us that direction. So if we know our total electric field as this diagonal right here, what's going to give us our electric field in the x direction? Why, it's going to be the electric field times cosine theta. Because if we do a little geometry, we know that this theta is the same as that theta. First thing I'm going to do is I'm going to ask myself, what is cosine theta? Cosine theta is adjacent over hypotenuse. In this case, cosine theta, even though we were interpreting it here, it's still going to apply here because our thetas are the same. Adjacent would be x over hypotenuse r. So we're going to rewrite cosine theta as x over r. Our electric field at point P is going to be the Coulomb's law constant K times the integral of lambda x dl over r to the third. Now, once we have our integral right here, we're trying to solve for electric field. Are we trying to solve for electric field as a constant? Are we trying to solve for electric field at an instant, at a specific point? Or are we trying to find electric field as a function of something? We're trying to find electric field at a point, as a constant. Therefore, we're going to need to evaluate a definite integral with bounds of integration. So we're integrating with respect to length. What did we say length was? Length was the total length around our circle, okay? So we're going to need to integrate from initial length all the way up to final length. Our initial length is going to be 0. And what's the total length of our ring? It's going to be the circumference, 2 pi a. Now I'm going to rewrite this integral with lambda put back into the derivation we gave it, equals k times the integral from 0 to 2 pi a of q over 2 pi a times x dl over r to the third. So now is when I do my integration. Now I need to identify what's constant, what's not. I know k is a constant. I had already pulled that out before. 2 pi is a constant. I can pull that out over 2 pi. A is the radius of my ring. Therefore, it's going to be a constant. I can keep that as 2 pi a. The total charge on my ring is a constant. The total charge on my ring isn't changing. That's going to get pulled out. X is the distance between point P and the center of the ring. Therefore, it's a constant. It's going to get pulled out. R to the third. Even as I change the position on my ring, the distance from point P to one of the sections on the ring is not going to change. Therefore, R third is a constant. It's going to get pulled out. Therefore, there's nothing left inside my integral. I'm just doing the integral from 0 to 2 pi a of dl, which is going to be L evaluated from 0 to 2 pi a, which therefore equals 2 pi a. Therefore equals k q x over 2 pi a r to the third times 2 pi a. This cancels with this, and I'm therefore left with k q x over r to the third. Do I need to change anything? It's in terms of k, x, and r, and universal constants k. Therefore, I am done. This is the electric field felt at point P in the r hat direction. Yeah, that's how hard it is. The thing I want us to know about this is a unique approach for this type of problem, meaning you're going to find a lot of different types of problems. You're going to find the electric field on a point charge contributed from charge distributed on a semicircle. You're going to need to find the electric field at a point from charge from a length of wire as such. And your geometric analysis of the situation is going to change each and every time. So I only have enough time to show you one example, the example with the ring. If you guys need more help, if you come across problems of different geometries that you don't know how to solve, I understand it's hard. Come join my Discord, come call me, come message me. I will help you. Okay, next topic is electric flux. Electric flux, we have an equation for on our reference table. It is given by the quantity phi, capital Phi, which is going to equal the integral of the electric field vector dotted with the area differential vector. So basically what flux is telling us is flux is asking how much electric field permeates through this area. So let's say I had a point charge right here and I drew a square some distance away from the point charge, that square being my area. I would be asked to calculate how much electric field permeates through that little square. Okay, and I would calculate the electric field at this point, and in this case the electric field vector is exactly parallel with the area vector. For just a reminder, if I were to draw a square like this, this is the square laying flat on the plane, then the area vector for any object is always perpendicular to the area plane, okay? So in this case, yes, electric field and the area vector are in the same direction. So cosine theta, it reduces to 1. And we just get this sum, and we just get electric field multiplied by the area of our square, side squared, whatever. That brings us to the much more interesting understanding of electric flux, which is Gauss's law. Gauss's law states that the electric flux is equal to the, of course, the equation that we were given before, the electric field vector dotted with the area vector differential, which is also equal to the charge enclosed by a Gaussian surface divided by epsilon naught. So what is a Gaussian surface? A Gaussian surface is a surface with a uniformly variable area that is exactly normal to a given charge surface. Let's give an example of what that is, because you probably didn't understand a word I just said. So if I have a sphere, okay, I have a sphere, pretend this is three-dimensional, that is charged, okay? It has some net charge plus Q, okay? If that is a sphere, then if I want to construct a Gaussian surface, I need to construct a surface that is exactly parallel to all surfaces of this sphere at all points. An example of the Gaussian surface for this would be a shell, a spherical shell around the sphere at the center, such that every edge of the sphere at the center is exactly parallel to every edge of the Gaussian surface. Therefore, the surface area of the Gaussian surface in this example would be the surface area of a sphere, which would be, I believe, 4 pi r squared, where r, of course, is not the distance from the sphere to the shell, it is the distance from the shell to the center of charge. So what Gauss's law states is if I calculate the electric field at a given point, or a differential area rather, and I integrate the electric field with respect to the area differential, I would get the total charge enclosed within this Gaussian surface, okay? So if I didn't know what charge was at the center, but I was able to gain the electric field, gain knowledge about the electric field, I could use this integral to determine the charge enclosed by the Gaussian surface. The hard part about this is when you are constructing a Gaussian surface that is not outside the sphere but inside the sphere. So again, I'm going to draw my sphere here, but I'm going to draw my Gaussian surface as within the sphere. So let's say that in this case I would have to be given a rho, which is a function of r, which is my linear charge density, dq dr. And my total charge enclosed would therefore, if you look at your reference table, this equation is present there. My total charge enclosed is going to be the integral of my density function with respect to the volume differential. Well, I have a function as a function of r, and I'm integrating with respect to volume. How does that work? Well, I need to change my differential, okay? First, we need to recall that the volume of a sphere is 4/3 pi r cubed. Therefore, if I were to differentiate this, the volume differential is 4/3 pi times 3r squared dr. These 3's cancel out, and we're left with 4 pi r squared dr. All right? Therefore, our total charge enclosed Q is going to equal the integral of our function rho, let's just call it 4r, equals 4r times 4 pi r squared dr. And that's how you find the total charge enclosed as you vary r, okay? And there are certain times where you're going to need to do a definite integral, sometimes you're going to need to do an indefinite integral. Sometimes you want to know the total charge enclosed at some radius. Sometimes you want to know charge enclosed as a function of r, and that's going to determine whether you want to do a definite or an indefinite integral. Thank you.